Geocentric Model. Long before anyone believed the Earth moved, ancient astronomers built an entire universe around the opposite assumption, that we were the center of everything and the sun, moon, and stars all circled us. The math actually worked for a while. To explain why planets sometimes seem to wander backward across the sky, astronomers like Ptolemy added smaller circles within circles called epicycles, stacking dozens of imaginary loops just to make the predictions line up. By the 1500s, the model needed so many overlapping fixes that even some of its defenders quietly noticed it was held together with duct tape. Then Copernicus proposed putting the sun at the center instead. And decades later, Galileo pointed a telescope at Jupiter and watched 4 moons orbiting something that definitely was not Earth. The geocentric model didn't fail because nobody tested it. It failed because with enough imaginary circles, you can make almost any wrong idea fit the data for over 1,000 years. Phlogiston Theory. In the early 1700s, chemists needed an explanation for why things burn, so they invented one. A fire-like substance called phlogiston supposedly lived inside flammable materials and escaped into the air during combustion. The theory explained rusting metal and burning wood with one elegant idea, and for almost 100 years it was the accepted framework of chemistry. The problem only showed up once people started actually weighing things. When metals burned, they didn't get lighter, the way you'd expect if some fiery substance were leaving them. They got heavier. 1770s and 80s, French chemist Antoine Lavoisier ran careful experiments in sealed containers and proved that combustion wasn't releasing a substance, it was absorbing one, oxygen from the surrounding air. By 1800, phlogiston was essentially dead in mainstream chemistry. Lavoisier would later be executed during the French Revolution, never knowing his oxygen theory would make him remembered as the father of modern chemistry. Caloric theory. For most of the 1700s, heat itself was thought to be an actual physical substance, a weightless fluid called caloric that flowed from hot objects into cold ones. It explained a lot of everyday observations and dominated physics textbooks for decades. Then, in 1798, a scientist named Count Rumford was overseeing cannon manufacturing in Munich and noticed something that didn't fit. Boring out the metal barrels generated enormous, seemingly endless heat through friction alone, with no caloric fluid being added or drained from anywhere. He immersed a cannon barrel in water while it was being bored, and friction alone brought the water to a boil in under 3 hours. If heat were a finite fluid stored inside matter, that shouldn't have been possible indefinitely. Decades later, James Joule's experiments confirmed it. Heat wasn't a substance at all. It was energy, generated by motion. Caloric quietly disappeared from physics over the next half-century. Luminiferous Aether. By the late 1800s, physicists knew light behaved like a wave, and waves, they assumed, need something to travel through, the way sound needs air. So they proposed an invisible, undetectable substance filling all of space, called the luminiferous ether. In 1887, Albert Michelson and Edward Morley built an extraordinarily sensitive device in a basement in Cleveland, floating on a pool of mercury to cancel out vibration, specifically to detect Earth's motion through this ether. If the ether existed, light should travel at slightly different speeds depending on direction. They found nothing. No difference at all. The experiment is still considered one of the most famous failures in the history of science. Except it wasn't really a failure. It was the first hard evidence that the ether didn't exist, and it helped set the stage for Einstein, who, in 1905, showed that light doesn't need a medium to travel through space at all. Plum pudding model. After J.J. Thomson discovered the electron in 1897, physicists had a new problem. If atoms contained negatively charged electrons, something had to balance that charge. In 1904, Thomson proposed that atoms were spheres of positive charge with electrons scattered through them like raisins in a pudding, evenly distributed, with no real structure inside. For a few years, this was the accepted picture of the atom. Then, in 1909, 2 of Thomson's own colleagues fired a beam of alpha particles at a thin sheet of gold foil, expecting them to pass straight through, since a diffuse cloud of charge shouldn't stop much of anything. Most particles did pass through, but a small fraction bounced back at sharp angles, some almost straight backward. Ernest Rutherford, interpreting the results in 1911, realized the only explanation was a tiny, dense, positively charged nucleus at the center of the atom. The pudding was wrong. Atoms were almost entirely empty space. Planet Vulcan. In 1859, astronomer Urbain Le Verrier noticed that Mercury's orbit wasn't behaving the way Newton's gravity said it should, drifting by a tiny but measurable amount every century. Le Verrier had already used this exact method to successfully predict the existence of Neptune. So when he proposed a new, unseen planet hiding in the sun's glare to explain Mercury's wobble, people believed him. He named it Vulcan and calculated its orbit down to the day. Amateur astronomers reported seeing it transit the sun. Professional expeditions chased solar eclipses specifically to spot it. Decades passed. Nobody could confirm a single sighting. Then, in 1915, Einstein's general relativity offered a completely different explanation. Space itself near the sun is curved, and that curvature alone accounts for Mercury's strange orbit. No extra planet required. Vulcan never existed. It was a phantom built entirely out of a math problem that needed 100 years and a genius to solve correctly. N-rays. In 1903, respected French physicist René Blondelot announced he'd discovered a new form of radiation he called N-rays, detectable using faint glowing threads coated in calcium sulfide. Within 2 years, nearly 300 scientific papers had been published about N-rays. They were reportedly emitted by metals, the sun, and even the human nervous system. There was just one problem. Almost nobody outside France could replicate the results. In 1904, American physicist Robert Wood visited Blondlot's lab and, during a demonstration in a darkened room, secretly removed the prism essential to the entire experiment. Blondlot's assistant reported detecting N-rays anyway. Wood published his findings, and the N-ray field collapsed almost overnight. It turned out Blondlot and his team had been seeing exactly what they expected to see, a phenomenon scientists still study today as a textbook case of how easily belief can outrun evidence, even among trained professionals. Steady-state theory. In 1948, astronomers Fred Hoyle, Hermann Bondi, and Thomas Gold proposed an alternative to an expanding universe with a beginning, a cosmos with no start and no end, where new matter is constantly created to fill the gaps left by expansion. So the universe always looks roughly the same on the largest scales. Hoyle, ironically, coined the term Big Bang while mocking the rival theory. For nearly 2 decades, the steady-state model was a serious scientific contender. Then, in 1965, 2 researchers at Bell Labs accidentally detected a faint, uniform microwave signal coming from every direction in the sky. It was the cosmic microwave background, the leftover heat from an extremely hot, dense early universe. Exactly what a Big Bang would produce, and something a truly steady, unchanging universe could never explain. Within a few years, most cosmologists had abandoned the steady-state model entirely. Cold fusion. On March 23, 1989, 2 electrochemists, Stanley Pons and Martin Fleischmann, called a press conference at the University of Utah and announced they had achieved nuclear fusion at room temperature, using nothing more than a palladium electrode sitting in a jar of heavy water. If true, it promised limitless, cheap, clean energy and would have rewritten the future of the entire planet. Newspapers ran headlines calling it the discovery of the century. Within weeks, labs around the world rushed to replicate the experiment. Most found nothing. A team at Caltech specifically searched for the radiation byproducts fusion should have produced and came up empty. By October 1989, a Department of Energy panel concluded there was no convincing evidence cold fusion was real. As recently as 2019, Google funded a multi-year, $10 million research effort hoping to finally find something. They found, in their own words, no evidence whatsoever. If you want to discuss this video or suggest an idea for the next one, comment down below and join us for a crazy world of explainer videos.